This is the another simple example. We can represent one function like this. G of capital G of j omega is equal to 50,000 times j omega plus 10 divided by j omega plus 1 times j omega plus 500. So here we have zeros and here we have poles. So always get the poles and zeros in a form such that the constants are associated with these j omega terms. So here we have, what is the constant value here? Here the constant is 50,000. So in the above example, we do this by factoring out the 10 in the numerator and 500 in the denominator. So we are keeping this 50,000 as it is. And here we have to divide by 10 everywhere. So 10 divided by 10 and j omega divided by 10. And here we have to multiply. So 50,000 times 10, and then you are dividing this whole term divided by 10. So then the term will be this complete. There will be no change, right? So I am dividing by 10, I am multiplying by 10. So if I cancel this 10 and 10, then this will be the original term. So just for some mathematical analysis, I am doing this. So 50 times multiplied by 10 and this one divided by 10. So what will happen here now? So here I have 500 as the constant. So 500. So then if I divided by 500, then I have to also multiply by 500. Then I will get the original term. So I do not really make any changes, but I am rewriting the equation differently. So 50 times 10, j omega divided by 10 plus 10 by 10 is 10 divided by 10 is equal to 1. And similarly, 500 times j omega plus 1, and then j omega divided by 500, and then 500 by divided by 500 is 1. So I represent like this. So I can make it more simplification. So this 0 0 is gone, and this 0 0 is gone, and this 5. So I can represent this 100 times j omega divided by 10 plus 1 and j omega plus 1. So the same equation I simplified, I wrote it in this way. So now when you have neither poles nor zeros at 0, start the Bode plot at. So here what is zeros, what are the zeros and what are the poles? In case if you do not really have any poles and zeros, then you have to start the Bode plot. 20 times log of k. K is the constant value. Here the constant value is 100. So log of 100 base 10. So that will be 40 dB in this example. So you are using this constant value, and then you are finding where the graph should start. So first what you had done, you are simplifying this equation. And then second one is like you have to find out the starting point of the graph. And now third one is observe the order in which the poles and zeros occur. This is the secret of being able to quickly sketch the Bode plot. So in this example, we first have a pole occurring at 1, which causes the Bode plot to break at 1 and slope minus 20 dB per decade. So we know that. So here we have these zeros. So zeros and poles. The pole is also occurring at 1. And we see zeros at occurring at, you can see here. We know that the numerator we have zeros and the denominator we have poles, right? So the first pole is occurring at 1. So that is why we are having this kind of slope. The slope is minus 20 dB per decade. Here in the zeros, it occurs at 10. So this causes a slope as plus 20 dB per decade. Then this both will get cancelled, right? Minus 20 dB and plus 20 dB. So the result is 0 flat line in the graph. Because something is causing minus 20 dB and something, the pole is causing minus 20 dB, 0 is causing plus 20 dB. So both will get cancelled then we will have a 0 dB line. So that means like this one and this one. And now we have finally we have a pole that occurs at omega is equal to 500 here, this one, which causes the Bode plot to slope down minus 20 dB per decade. So you have to do this kind of analysis by yourself manually before you start to plot the Bode graph. So now we are ready to plot or draw the Bode. So before we draw the Bode, we should observe the range over which the transfer function has active poles and zeros. This determines the scale we pick up for omega. At the bottom of this Bode plot, we know that omega is going to be in the x-axis. So we need to also select the correct scaling. You divide by 10, 10, 10 or 20, 20, 20 or 100, 100. So you have to select the correct scaling. Similarly, for the y-axis also, in terms of dB, you have to select the correct scaling. So the dB scale depends upon the magnitude of the plot, and experience is the best teacher. So you have to solve this kind of problems, many problems, then you will have more ideas how to plot this kind of magnitudes and phase angles. Now we are talking about the magnitude. So what we had seen, this is the actual original function. First, I do simplify this function, and then the second, I have to find the starting point of the graph. Third, I am analyzing one by one where the graph is going to be flat, where the graph is going to rise, where the graph is going to fall, like that. So based on that, this is really based on this function where I have found. So now if you see, if you really plot the graph will look like this. So here we are starting in 40 dB. Remember, we calculate the starting point. The starting point is 40 dB in this case. So we are starting from 40 dB. It's coming in the first part of the graph. So this is 0 and then the minus 20 dB per decade, and then 0 flat again, and then minus 20 dB per decade. So this is how we have to do the plotting or plot the graph by using Bode. So, and of course, if you are really interested more, you can also run this in the MATLAB. You can install MATLAB, and for students, it's a free version. You don't need to pay anything to install this MATLAB library. In the MATLAB, actually, we can do different kind of simulations. You know, Simulink, if you are a power electronics student, in the third year, when you take the power electronics course, you will have to do this Simulink and SimSpace. SimSpace is just a library name. Simulink is also kind of libraries. These all are coming under MATLAB. You know, MATLAB, you can write the program like this. I had given here the MATLAB program. If you really want to explore more about these frequency considerations, you can use this program, or you can take this kind of several functions, and you can write the program, and you can see how the system is plotting the graph automatically. So you know, system, they don't care about, they don't need to do this kind of steps manually. They do automatically, they plot the graph. You can also check that, and you can do the manual things, and then you can compare your manual plotting and the graph plotted by the system using MATLAB software. Okay, this is one way. And the other way, Simulink and SimSpace, you can represent the system in terms of models. So for example, let us say you have some kind of filter circuit. You have capacitor, you have resistor, and you are applying input and you are getting output. So they have the library. So you can get the capacitor as the capacitor, and you can choose whatever the value you want. For example, you want to have 10 nanofarad. You can set up the value by yourself. And the resistor you can pick up from the library like this. Just drag and drop, and then represent, and this may be 100 kilo ohms. And input, you can also take the input source. It will be like this, maybe something like this, plus minus and you can select how many what magnitude you want to apply. Maybe you want to apply 10 volt, and then the frequency may be 50 hertz or 60 hertz, whatever. And then you can have the oscilloscope. You are using in the electronics lab already, the Vigilant kit. So this MATLAB Simulink is little more also advanced or similar type. So you can have the software based scope. The scope will connect to these two terminals and it will show the graph, whatever the output graph it is. So you are modeling the system, the complete LPF low pass filter system in this MATLAB using Simulink. And then you are observing you are performing the simulation and checking the output response. So this is one way to do Simulink. So if you are really interested, you can download this MATLAB. When you download the MATLAB, please enable the libraries for Simulink, SimSpace, and all other libraries. You just enable it. So you will have all the functions and you can perform this. And instead of using these libraries, you can also use MATLAB directly and you can write this kind of programs. And also you can observe the frequency response. So the Bode plot will look like this if you write that program. So this is for the previous problem, this problem. Okay, so now comments, phase for Bode plots. So so far we talked about the magnitude. Now the phase. Generally, where is my cursor? Generally, the phase for a Bode plot is not as easy to draw or approximate as the magnitude. So we can use analytical method for determining the phase if we want to make a sketch of the phase. So remember, we represent the transfer function with this angle G of j omega is equal to the formula. We had seen 5 different cases. The formula is like this: tan inverse omega by the constant. So omega divided by 10 minus, this is just for the same example, the previous example. Remember, this is what we simplified in the previous example. Where is my pen? This is the function. This is the transfer function we have simplified. I will show you again. So this is the original problem, and we simplified this like this. So I'm taking the same problem now to plot the phase angle. So the phase angle, tan inverse omega by 10. This is omega by 10, right? And then minus tan inverse omega divided by 1, and then minus tan inverse omega divided by 500. So now I have to find this one, and that is the phase angle of this transfer function. So we are essentially taking the angle of each pole and zero, each of these expressed as tan inverse imaginary part divided by real part. Imaginary part divided by real part. So j part divided by real part. So here, for example, this is j omega divided by 10. So this is the imaginary and this is the real. Okay, so usually about 10 to 15 calculations are sufficient to determine the phase angle, or just to analyze the phase angle. So far we have completed the frequency considerations. So this is the summary. Bode plot is a, where is my cursor? Bode plot is a frequency domain technique in which magnitude and phase are drawn in graphs. Graph 1, the magnitude of the transfer function as a function of frequency. So remember, this is the first part of the graph, or we can also call this as a graph 1. And the graph 2 is the phase angle, that is the pi, as a function of frequency. Here is opposite. So omega is equal to 2 pi f, that you should remember. So this is how the Bode plot is constructed. Just for an example, okay, Bode plot consists of two subplots, which are a magnitude plot and phase plot. So the first part here, you can see here, this is the magnitude plot and this is the phase plot. By combining this magnitude plot and phase plot, we can get Bode plot. This complete one is called Bode plot. Both plots have same x-axis. That is here, for example, the same x-axis, frequency, that is the 2 pi f or omega, simply we can call. But different in y-axis. Here we have the magnitude in terms of dB, and here we have the phase angle in terms of degrees. And for magnitude, y-axis is the magnitude of the open loop transfer function, VO divided by VI, or A in dB. And how to calculate the magnitude, you already know the formula. So you already know how to calculate the open loop transfer function. And then after calculate the VO by VI, that is the transfer function. And then you have to calculate the magnitude by using this formula, 20 times log base 10, whatever the value. The unit is decibel. How to calculate the phase angle? Phase angle is equal to tan inverse J part divided by real part. It means J means imaginary part divided by real part. Unit is degrees. So I think we are done with the frequency considerations.